Hello calculus fans. Today we are going to look at the tangent and velocity problems, which should give us some insight into how differential calculus was developed. We'll spend a lot of time initially talking about limits. The concept of a limit is a fundamental building block on which all calculus concepts are based. It's one of the ideas that distinguish calculus from other branches of math, like algebra, trigonometry, and we're going to develop the concept of a limit in stages, proceeding from an informal, intuitive notion to precise mathematical definition. In this section, we're just going to see how these limits arise when we attempt to find a tangent line to the curve or the velocity of an object. In considering the tangent problem, what we're going to do is start off with a problem you would have seen in a typical algebra class. So it says find the equation of a line parallel to this line and through this point here, the point 1, 2. So as I said, this is sort of a typical algebra problem. I want to find an equation of a line. Well, in the equation of a line, when you see this equation of a line, we could put this in slope-intercept form. All right, y equals mx plus b. So when we're all done, our answer will look just like this. So basically we need to find the slope m and the y-intercept b. Well, to find the slope, just remember that we're finding an equation of a line that's parallel to this line. So since our line will be parallel to this line, our line will have the same slope as this line. So really we just need to know what's the slope of this line, because if we know the slope of this line, then we know the slope of our line since they're parallel. So in order to do that, what we could do is just solve this equation for y. Because if we solve this for y, then it will also be in slope-intercept form, and then we can just look at the slope. So to solve it for y, we need to basically get y by itself. So just think of the good old days in algebra class. To isolate this y, I'm going to add 9 to each side of the equation. So that would cancel. And that would give us 2x plus 9 equals 3y. And then we want to get y by itself, so we divide by 3, divide each of these parts by 3. And that would give us 2/3 x plus 3 equals y. Well, all we really care about here is the 2/3, right? That's really all we care about. So what we've done is we've just taken this line and we put it in slope-intercept form. And now that it's in slope-intercept form, we can see the slope is 2/3. So our line, which is parallel to this line, our line will also have a slope of 2/3. So I could take this 2/3 and basically plug it in right here for the slope, right? So we know the slope of our line is 2/3. Now we just need to find b. And we can find b by using this point. So let's go ahead and just find b a second. So to find b, I'm going to use this equation, y equals mx plus b. I'm going to take this 2/3, the slope that's 2/3, I'm going to plug it in for m. And remember that if this point is on our line, then this point would satisfy our equation, right? It would satisfy our line. So if I plug in 1 for x and 2 for y, I should get a true statement here when I solve this, and that's going to allow us to find b. So what I'm going to do is take this point 1, 2. I'm going to plug this in for x, that in for y, and then solve for b. So that would give us 2 equals 2/3 times x, which is 1, plus b. So 2 equals 2/3 plus b. So to get b by itself, I subtract 2/3. So I basically have 2 minus 2/3 equals b. Well, this 2, really this is 6/3, right? 2 could be 6/3. So 6/3 minus 2/3 is 4/3. So b equals 4/3. So that implies that b equals 4/3. So now we know what the slope is, and we know what the y-intercept is, so we can write our answer. So the answer we're looking for is y equals 2/3 x plus 4/3. So what we just found is we found an equation of a line parallel to this line and through this point. And you can see with this problem we needed no calculus. All we needed was basic algebra. So for example 1, the only thing we need for this problem is algebra. So let's try example 2. Example 2 is also a kind of a typical problem from an algebra class. Find the equation of a line through these 2 points. There's a reason why we're doing some review here from algebra, because when we get to example 3, we're going to see a problem that algebra won't be able to solve. So we'll need something else. So for this one though, we've got an equation of a line through these 2 points. So again, they say equation of a line. Equation of a line, so we're going to think y equals mx plus b, which means we need to find 2 things. Find the slope, find the y-intercept. And you probably remember from the fun-filled days of algebra class, you had the slope formula. The slope formula for the slope of a line through any 2 points. Who remembers this one? Maybe it'll sound familiar. y2 minus y1 over x2 minus x1. Remember that one? So we can use this formula to find the slope of a line through these 2 points. And again, when you use this one, for a little review here, it doesn't matter if I call this point 1 and this point 2, or if I call this point 2 and this point 1, it doesn't matter. The only thing that matters is if I say let's say I call this point 1. So this would be x sub 1, y sub 1, x sub 2, y sub 2. So if I use the formula and I start with this 6 and call this y2 and I go y2 minus y1, well, if I start with this 6, then I have to start with this 3. That's the only thing that matters. It doesn't matter which point I start with, as long as I'm consistent. So if I start over here with this 6, I'm going to go y2 take away y1, right? So you just go 6 take away 4. And then because I started with this 6 here, I need to start with this 3. So I go 3 take away 2. So this gives us 2 over 1, or just 2. So the slope is equal to 2. And if you had started the other way and went 4 minus 6, 2 minus 3, you get the same thing. You just get a negative over negative, which is a positive. So we get the same slope regardless. So now we know, so far we know that the slope is 2. So now we need to find b. Just like before, we can find b by just plugging in values into this formula. We've already got one of the values. We know the slope is 2, so I'm going to plug a 2 in there. And then for the x and the y, I just need 1 point. I've got 2 to choose from, and it doesn't matter which one we pick. We're going to get the same answer. So typically just pick the one that's easier to work with. In this case, they're both pretty easy. I'll just pick this one though. I'll pick 0.2, 4. So I'm going to choose this one. So I've got x and y. And now I just plug this in to solve for b. So I'll get 4 equals 2 times 2 plus b. 4 equals 4 plus b. So subtract 4 from each side. And of course, we're going to get 0 equals b, or b equals 0. So the y-intercept is 0, which just means this line goes to the origin. So the answer to the question then would be y equals, we know the slope is 2, and then plus b, which is just plus 0, so you typically wouldn't write that. I suppose you could write y equals 2x plus 0, but normally we would just write y equals 2x. So far, the first two examples, we have not needed any calculus. We just needed algebra. So there's really nothing new at this point. But with example 3, we're going to see that algebra is not going to be enough to have us answer this question. This question wants us to find the equation of the tangent line to this parabola y equals x squared at this point p 2, 4. Well, the parabola y equals x squared, we've all seen that hundreds of times, I'm sure. Y equals x squared, the parabola opening up goes right through the origin. Now, tangent line. We need to talk about a couple of terms we're going to see here, tangent and secant. So let's just mention a tangent line. Tangent, think of this as like just touches. Okay, and I'll explain that with a picture. It's from a Latin word which means to touch. And then secant, when you see hear this term secant, think of this as cuts twice. And these ideas, just touches and cuts twice, will work for us. This is really what we need. And secant is from the Latin word which means to cut. You can think of this maybe as like it intersects the line twice. We're going to talk a lot about tangent lines and secant lines. And when I have a picture, it'll be easier to describe and explain both of them. But just remember, for now, these are not the right triangle trig words. It's not like tangent, we sine, cosine, tangent. It's not that. These are from geometry, so they're not from right triangle trig. So tangent is a line that just touches a curve, and the secant is a line that's going to cut the curve twice. So as an example, let's take a look at this line this curve y equals x squared. So here is a picture of y equals x squared, a parabola we've all seen hundreds of times. And we want to find the equation of the tangent line to this parabola at this point 2, 4. So we've got this point right here, this point 2, 4. You want a tangent line to that point. So tangent, it just touches the line. It's actually going to be a little bit tricky to draw this, but I want this like straight line, just tangent to the curve right there. So just tangent. So if we're going to try to find the equation of this line, well, if you think about the other two problems, we had a way to find the slope. But in this case, we don't have a way to find the slope of this tangent line. So we are not going to be able to do either of those previous techniques. So to get a handle on this, let's just think of blowing this picture up and moving it over here. And I'm also going to exaggerate the curve a little bit just so we can get something to talk about. So let's say the curve that's the y equals x squared curve. And let's say this is this point P, this point 2, 4. We want this tangent line that just touches the curve and it shoots off like this. So this is this point P, which is 2, 4. And what we want to do is try to figure out the slope of this black line. And we can't use the slope formula because we've only got one point. We don't have that second point. So we can't use y2 minus y1 over x2 minus x1. And so we've got to come up with some other way. So the way that we could approach this is we could think of, let's call this other point Q. We're going to call this point Q. And this would just be some point x comma x squared, right? Because this blue curve is the curve y equals x squared. So y equals x squared. So if this is 3, this would be 9. So the point 3 comma 9 would be on there. And what we want to do is think of this. Let's say I'll make this a red line. This red line that goes through the point PQ, we could find the slope of this red line because we could pick a couple of points. Now this slope of this red line is not really the slope that we're looking for. So what we're going to do is we're going to slide this point Q down the curve until it's closer and closer to this point P. So it's really difficult to see here, but we're going to basically approach this. The x-coordinate is going to approach 2. So we got this 2 over here, and of course this is 4. And our x-coordinate is going to approach 2. So our q will sort of, as x approaches 2, q will slide along this blue curve. So it's going to slide along here as this x-coordinate gets closer and closer to 2. So we could see that the slope of this red line is not really what we're looking for. We want the slope of the black line. The black line is a tangent line. It just touches, right? Just touches. The secant line cuts twice. This secant, we can find the slope of the secant line if we plug in an x value here. And the secant line cuts the curve twice. It cuts through y equals x squared twice. And then what we're going to do is slide this x-coordinate closer and closer to 2. So maybe we'll have another point that's right here on the blue line. And then that secant line, if I go through that curve, or go through those 2 points, this curve, or this new red secant line, is closer to the slope of the black tangent line. And as we get closer and closer here, think of this point Q that's like right next to this point P. It's right next to it. So the slope through those 2 points is going to be really close to the slope of the black line that we're looking for. So that's the idea. So with that in mind, we can go back and use our slope formula here. We'll say the slope through this point PQ, the slope of the line through the point PQ, and we know it's y2 minus y1, right? y2 minus y1, right? y2 minus y1. So that is going to be x squared minus 4 all over x2 minus x1, which should be x minus 2. So this formula right here is just our formula from geometry. The difference is now we've got a variable here. And this will work as long as x is not equal to 2. Because, of course, if x equals 2, then we're going to get division by 0, and that would be meaning this point Q is the same as the point P. Right? We want to slide x along here closer and closer to 2. We could go from numbers below 2 also. This one just happens to be from above 2. And as this slides along here, we want to see the slopes of these secant lines, and we can see they're going to get closer and closer to the slope of the tangent line. A nice way to see this is to use a graphing calculator. Instead of trying to calculate all of these slopes by hand, if we go to the graphing calculator, we go into y1 and we store in this slope formula of x squared minus 4 over x minus 2, and then we can just have the calculator plug in all these values for x and figure out what the slope is, because remember, this is actually the formula for the slope. This value here is actually the slope of the line through the point, through P and Q. It's the slope of the secant line. And what we can do is we can look and see what happens as x gets closer and closer to 2, coming from below 2, and also as x gets closer and closer to 2, coming in from above 2. And maybe we can guess what would happen at 2. So what we want to do, we want to fill in this table here, but we don't want to actually go through by hand and plug in 1.5 here and 1.5 here, and then 1.9 here and 1.9 here. So what we're going to use is we're going to use the table function of a graphing calculator. We're going to use the TI-8384, and that allows us to fill these in, except for 2. We can't plug in a 2 because we'll get division by 0. But what we want to do is see if we can see what these numbers are approaching, and maybe we can make an educated guess at what the slope would be right at 2. Or in other words, what is the slope of that tangent line right at 2? Maybe we can make an educated guess by seeing if these numbers approach a single number. So let's take a look at the calculator and see if it can help us. So to use the table on the TI-83 or 84, let's just go to y equals, and then type in our slope for y1. Also, make sure that your plots are all not highlighted up here. Make sure none of those are highlighted. If they are highlighted, For instance, if you see this, you want to just turn that off. So go up to the plot, hit enter, and come back down. And what we need to do is type x squared minus 4. Make sure you put that in parentheses, divided by x minus 2. So that'll give us our slope formula. And then to use the table, we have to go to this table up here. So you go second table, and then we can plug in values here. So I'm going to delete these. Now it could be that when you go to the table, you have a whole bunch of values here and you can scroll, but you can't delete. If that's the case, go to above the window, it says table set, go to second table set, and make sure this independent variable is on ask. You want that to be on ask and dependent to be on auto. And then once you do that, then we should be able to go to the second table and punch in anything we want. So we could type 1.5 and get our y1, which is our slope of 3.5, and you go to 1.9, we'll get 3.9, 1.99, and so forth. We can see that it looks like the slope is approaching 4 as x gets closer and closer to 2. But it looks like it's getting really close to 4. So those are values lower than 2, or values below 2. But if we approach from values above 2, like 2.5, 2.1, and get closer and closer to 2, but a little bit bigger than 2, you can see also it looks like our y value, which would be our slope, looks like that is also approaching 4. So just to remember what we were just trying to do, we're looking at the slope, we're trying to find the slope of this tangent line, this black line here. And because we just have a slope formula from algebra that requires 2 points, not just this 1 point, this point is 2, 4. Because we need 2 points, what we've been doing is finding other points on the curve y equals x squared by using x coordinates really close to 2 on either side of 2. So we came in values here above 2, which you can see on the picture here. These were values above 2, and it looked like the slope was approaching 4. As we got closer and closer to 2, we picked these tangent lines where this x value is really close to 2 but a little bit bigger than 2. We found the slope of the secant red line. And then we do the same thing over here with values less than 2. So some of these points up here that were less than 2. And it looks like in both cases we can see a pattern emerging. And we can see the pattern just by looking right here. As x gets closer and closer to 2 from values below 2, so coming in here from the left, the slope of the secant lines get closer and closer to 4. And also same on the other side. As we approach 2 from the right, from values bigger than 2, these slopes get closer and closer to 4. So if we had to guess, and we are guessing, it looks like probably the slope of that tangent line is 4. Now, again, we're just making an educated guess, but probably the slope of this black tangent line is 4. Also, something that we mentioned, but just to make it official for this little note here, it doesn't matter which side of 2 we approach from. You can see that by looking at our table. So whether we approach 2 from the right or from the left, from values above 2 or from below 2, it didn't matter. We were still heading towards 4. And now here's the important concept that we have been heading for from the beginning. The slope of the tangent line, slope of this tangent line, the slope that we were looking for, it's the limit of the slopes of the secant lines. This concept of limits is going to be really important for us, but we can see just by looking at these numbers, it looks like these numbers are heading for a value. Like the limit of these secant slopes seems to be 4, again from either side. So in other words, the slope of the tangent line m equals, here's the notation that we'll see. This says the limit as x approaches 2. The limit as x approaches 2 of this expression, which seems to be 4. And another little note here, this note is we have not proven the slope is 4. Not proven that the slope is 4. Now it is actually 4. When we get a little more experience here, we'll show that the slope is 4. But at this point, we're making an educated guess. We're doing that because that's all we've got. We don't know calculus yet. We just know algebra. So we're using algebra and basically making an educated guess. And at this point, we can actually find the equation of the tangent line to the parabola because we are looking for this equation, y equals mx plus b, right? Equation of the tangent line. Remember, the tangent line is just the line that just skims the curve at that point 2,4. So it's at the point 2,4. And there's a couple ways to do this. So we've done it this way before, where we plug the slope in here for m, and then we use 2 and 4 to get this. Some of you have also learned this other way, and I want to use this other way also. Some of you learned this technique where you go y minus y1 equals the slope times x minus x1. And this is called point slope form. You have the point x1, y1 and the slope m. And you can use this too and just plug values in here and solve for y, and you'll get back here. So I'm going to do this problem with this equation just because I know some of you have learned it this way. But the other way works too. So if you're more comfortable with this, you go ahead and you take the 4, plug it in for m. You take this 2 for x, that 4 for y, and you plug those in and you solve for b. If you do it this way, what we do is we take the slope of 4, that's going to go in for m, and we use this x1, y1, x1, y1, and then we just plug these in. So with this technique, you'd get y minus 4 equals 4 times x minus 2. We basically solve this for y, so I have to distribute through here. You get y minus 4 equals 4x minus 8. Then we add 4 to both sides, and we get y equals 4x, negative 8 plus 4 gives us minus 4. So that is the equation of a line that is tangent to the parabola at the point 2,4. So what I'm going to do now is I'm going to graph both of these. I'm going to graph this line, and also I'm going to graph the parabola y equals x squared. So on the calculator, what we'll do is we'll go to y1 in the graphing calculator and put x squared. y2, we'll put 4x minus 4. And to make it easy to see, let's change the window. Let's make on the window, let's make x go from 0 to 3. And we'll make y go from 0 to 9. And when we do that, we should be able to see, we should at least get a reasonable picture where it should look like this line is just tangent to the parabola at that point 2,4. So if you go ahead in your graphing calculator and punch these in, we'll see first we've got just x squared and 4x minus 4. Over here I set the window, and then here's the graph. So because of this window, it's sort of stretched out a little bit. You can see y equals x squared right here. And you can see that this is 1, 2, 3. So this is point 2,4. You got this straight line, which is the tangent line to the curve. So it at least looks reasonable. It looks like this line 4x minus 4 is in fact tangent to that curve. Remember, tangent means it just touches. So at least the picture seems reasonable. So that takes care of the tangent problem, where we try to find the equation of a tangent line to a curve at a particular point. I noticed me talking about calculus seems to make these two very sleepy. I hope it does not have the same effect on you guys. It doesn't, right? Right? You guys still awake? Okay, hope you're still awake, because now we have to look at the velocity problem, which is actually the same problem, just rephrased a little differently. The velocity problem has to do with trying to determine how fast an object is moving at an instant in time. Galileo was one of the first experimental scientists. And up until that time, Aristotelian physics ruled. So there was about a 2,000-year period where Aristotelian physics were the accepted physics, where he believed that the Earth was the center of the universe, the sun revolved around the Earth, and that heavy objects fell faster than light objects. And his physics was based on things that seemed to be true to everyday experiences, but they weren't really set up to be tested. Where Galileo, he was more of an experimental scientist, which really up until that time was not really done. And Einstein and many others have called Galileo the founder of modern science. And just interestingly, he died in 1642, which was the same year as somebody very important to calculus was born. That'd be Isaac Newton. Galileo, he used telescopes to look at the moon and saw that, contrary to what Aristotle believed, the moon was not a perfectly smooth object. It had craters and mountains, and he just saw that the moon basically was not a perfect smooth sphere. He also noticed that if you took parchment, like a flat parchment, like a piece of paper, and you drop it, it falls slowly through the earth. But if you take that same parchment and crumple it up and then drop it, it goes faster. So he knew there was something there that Aristotelian physics didn't take into account. It was air resistance. So Galileo brought this experimental science into view, and we no longer just accepted things on face. We wanted to experiment and see if beliefs were true or not. And he found that the distance fallen by a free-falling body is proportional to the square of the time it has been falling. And this is neglecting air resistance. And this can be expressed by what's called a position function. Which we've got listed right here, which says that S of t equals 4.9 t squared. Now this is in meters. Galileo first established this position function using inclined planes and his pulse. As you can imagine, this time period, the watches that were in existence, they were not in existence. So the best he could do was use his pulse. And then to slow down a dropped object, he used inclined planes. So he would roll a ball, let's say, down a plane that was inclined maybe like this. And then he would incline it a little bit more, and then a little bit more. And you just see like the time it took the ball to roll down the plane. Then you'd think, okay, so if it were dropped straight down, how fast would it go? And in doing that, he came up with a fairly accurate model here. This one here is using meters, so this would be in meters. And if you used feet, then you would have this model, S of t equals 16.1 t squared. And these numbers are both based on acceleration due to gravity. So to see how this works, let's suppose you go to the top of the Willis Tower, or the Sears Tower, which is 1,450 feet tall, And I know you would never drop any of your math books because you keep those forever and ever. I understand that. But let's say, let's just say maybe it's your, I don't know, your English book. Okay. There's no English majors listening. So just the thing I thought of off the top of my head. I just know it wouldn't be a math book. So we've got the Sears Tower, Willis Tower, 1,450 feet tall, which is pretty short compared to the Burj Khalifa in Dubai, which is 2,717 feet. Just think about how tall that is. That's a Burj Khalifa, I guess it's called. Now in Grand Rapids, Michigan, the River House condos are the tallest at a mere 412 feet. But we are talking about a building which is 1,450 feet tall. One of the interesting things about large buildings, one of the big engineering problems, is how to make a building not be just elevators. If you think about this building in Dubai, it's 162 stories. There are thousands of people in that building every day. How do you get people to 162 stories without making the whole building elevators? And it was actually a difficult engineering problem. To make this work, we need to start off with a formula that you've seen plenty of times. Distance equals rate times time. What we're going to use, though, instead of rate, we're going to use velocity. Distance equals velocity times time. And, of course, if this is true, we could divide each side by t to solve for velocity. So velocity would be distance over time, which is the one that we're going to use. So we've got the formula up above. We've got our position function, s of t equals 4.9t squared. So the way this works, we plug in the time and it will give us the distance, right? This is our position. So to give us the distance, this is fallen, and of course we're ignoring air resistance. But adding air resistance just turns out to be one more term. So like everything, we'll learn the simplified way first, and then as we get comfortable with that, we'll add in more detail to make it more realistic. But we'll start off ignoring air resistance. So you got our position function, and we could figure out, so we want to know, find the velocity of the book after 3 seconds. Well, let's see where the book will be at 3 seconds. So let's use our formula here and figure out where will the book be after 3 seconds, like how far will it have fallen. So we plug in 3 for t and we square that, and if you do the math here, you'll get 44.1 meters. So just remember this here, this is distance, right? This is the distance. The book will have fallen 44.1 meters at that 3 second mark, right? After 3 seconds, the book will have fallen 44.1 meters. So what we could do, we could think of this average velocity. And put a v with a bar to mean average. So the average velocity, well, using this formula right here, distance over time, the distance 44.1 meters, the time 3 seconds. So the average velocity would be 44.1 meters over 3 seconds, or 14.7 meters per second. So one thing we have to note here, though, this is not really what we're looking for. We want to know the velocity of the book right at 3 seconds. We're finding the average velocity over the first 3 seconds. But we know when we initially release that book, it's going 0 meters per second, right, initially. And then we know it's going to pick up speed. So this is the average of the first 3 seconds. But right at 3 seconds, it should be going faster than this. So this is what we have to be aware of. This is not instantaneous velocity. Right? It's not instantaneous velocity. What this is the average velocity over the interval from 0 to 3 seconds, which again, it's not what we're looking for. We want the instantaneous velocity right at that 3-second point. We've got the average velocity so far. Let's talk about this average velocity for a second here. So this V naught or V bar, this average velocity, this is equal to the change in position over the change in time. Now this change in position, in your physics class, when you're dealing with vectors, you'll call this displacement. We don't talk a lot about displacement in calculus, because in calculus 1 and calculus 2 we don't have vectors. But you'll see change in position is often referred to as displacement. But basically the average velocity is just change in position over change in time. And we've got a couple formulas that you'll see when it comes to average velocity. I'm going to write these down, and then you'll see basically these are just the slope formula from algebra class. It's really the same exact formula. So this first formula here, this is saying that the average velocity is the final position minus the initial position divided by the final time minus initial time, which is basically this, the change in position over the change in time. You also see it written this way sometimes. Average velocity, you'll see this ARC, average rate of change. Sometimes you'll see a function referred to as the average rate of change. And this is just f of b minus f of a all over b minus a. Now, these really are the same formula. They're the same formula with just different notation on your graph. And they are both the slope formula. This is the slope formula. This is y2 minus y1 over x2 minus x1. And this also is y2 minus y1 over x2 minus x1, just with your x and y axes labeled differently. We can see that right here from this picture. We'll see that the slope formula from algebra results in this formula here. If we label the position versus time curve like this with an A and a B, we could label a little bit differently and get this formula because they both are just the slope formula. So with this labeling, this point here is a point A and f of A. And this point here would be the point B and f of B. Right, because we've got, this would be the x-coordinates here, x-coordinates. The y-coordinates would just be what you get when you plug these values into the function f of t. So if we wanted to find the slope of a line through these 2 points right here, these 2 points here, we could go like this, find the slope of the line through those 2 points, and we could just do kind of like we've done before in algebra class. You got the rise right here, right? This is the rise over the run. Slopes just rise over run. And if we use the slope formula, y2 minus y1 over x2 minus x1, we use this formula here. Y2 is going to be f of b minus y1 is f of a, which is right here, f of b minus f of a, over x2 minus x1 over b minus a. So this is just the slope formula. With a position versus time curve, though, that slope formula gives the average velocity. And the same thing here. If I label these a little bit differently, instead of A and B, if I have initial like I here and F for final here, then this is the position and the time, and then I use the same formula. I'll just get average velocity equals this. So both of these average velocity formulas, we've seen them before. They're just the slope formula. It's just a quick recap of what we've done. We found the average velocity for the time interval from 0 to 3 seconds. Okay, but that was an average velocity. What we really want to do is shrink this time interval. So instead of from 0 to 3 seconds, maybe from 2.99 seconds to 3 seconds, or maybe from 3 seconds to 3.01 seconds. But we want this gap to be much tinier so that we can get an approximation of instantaneous velocity. So in order to do that, we'll do something that's going to look a little similar. So let's say we've got this position function, s of t equals 4.9 t squared. And let's just maybe sketch a little picture of that right here. And what we want to do is approximate this rate of change right at 3 seconds. So right at 3 seconds here. So this is 3. Now this graph, the scaling is definitely different, right? Because if I put a 3 in here, it'd be way up much higher. So the horizontal axis and the vertical axis are scaled differently. But it would have this general shape, right? It's still a quadratic. So we'll do the same thing again. We'll imagine that we're going to zoom in right here. We're looking for this tangent line here. But what we're going to do is we'll blow this up over here. And once again, I'm going to exaggerate the curve just so we can make some sense of it. So I'm going to exaggerate this curve. And let's say we are going to focus at 3 seconds. So this would be at 3, and then the y here, if I plug in a 3 here, I have to find the y coordinate. 4.9 times 3 squared would be 4.9 times 9, which turns out to be 44.1. So this point right here is really the point 3 is the x coordinate, and the y coordinate is 44.1, right? Remember I mentioned the scaling is definitely different. So what we're going to do, though, for our example, we are going to come in from values a little bit bigger than 3. We're going to approach 3 over here to get another point up here on the curve. So it'll look like this. Here's our other point, which we'll just call this point x, and then 4.9x squared, right? Because here's our function. So whatever I plug in for x, I'm going to go 4.9x squared to get the y coordinate. So again, what we really want, we want this slope of this tangent to the curve right there. We want this slope of this black line that just skims the graph. Well, what we'll do instead is we'll find the slopes of these red lines, of these secant lines, but then what we'll do is we're going to slide this closer and closer to 3, and as that happens, this point will slide closer and closer to that point. So we could find the graph of this red line here, and then we'll come a little bit closer, so we'll use this point here. This will be our new x-coordinate. So then we'll find the slope of this red secant line there. Well, that slope of that red line is closer to the slope of this black line. And then we'll slide it even closer. So we'll slide this point a little bit closer along the curve, find the slope of that secant line, which is getting really close to the slope of the tangent, and we're going to do the limiting value. So we'll do something very similar to what we've done before. We have the slope formula, y2 minus y1 over x2 minus x1, because we're really going to look for the slope of the line through 2 points, right? Through like this point and then that point and that point. We're going to keep getting closer and closer to that point right there. So if I plug this in, here's y2 minus y1, x2 minus x1. So from our slope formula, we will get 4.9x squared minus 44.1. Remember, this 44.1, that comes from plugging 3 in here, right? When t is 3, I guess I've been calling it x, but when the independent variable is 3, y will be 44.1, or s of t will be 44.1. So over here, we're going to have x minus 3. And just to make sure we're okay on this one, this is 4.9 times 3 squared. So what we want to do with a graphing calculator then, just like before, we're going to plug this in for y1. So in the graphing calculator, we would say, okay, y1 equals 4.9 x squared minus 44.1, parentheses, and over here we'll have x minus 3. And looking at this formula here, you notice that using this picture, if we think of this as position versus time curve, there's another formula that sort of comes to mind here. This average velocity formula, which is just the final position minus initial position divided by final time minus initial time. This really is the same formula. We're thinking in this case is the initial time being 3 seconds, and the final time is just a little bit more than 3 seconds. So this really is just this formula here for average velocity. So let's take a look though and see how this works on the calculator. Now keep in mind though, our initial time is 3, right? Our initial time is 3 here. So let me just make sure we're clear on this. So we're going to start, in this case, if we use this, I equals 3. Initial time is 3. Final time will be maybe 3.1 seconds or 3.01 seconds or something like that. So what we want to do now is, like before, we want to put this in the graphing calculator for y1. Put this for y1, and then we want to go to the table. And when we look at the table, just keep in mind these are initial times. So our final times are these. These are the times you want to plug into the calculator. These are our final times, right? Initial time is 3. Final time is these just one at a time. So we plug these in. And if you plug this in for y1 and you go to your table and you plug in a 4, you're going to get the average velocity between 3 and 4 seconds. And your calculator should tell you 34.3. And then if you plug in 3.1, we get 29.89. And if you keep going here, we should get 29.449. And then finally 29.4049. And if you get even smaller here, 3.0001, or if you go on the other side of 3, these are all values bigger than 3. We could just as easily have values less than 3, like 2.9, 2.99, 2.99. But you should notice the same pattern. It looks like we can make this as close to 29.4 as we want to. So just looking at this right here, it appears that as we shorten the time interval, the average velocity is becoming closer and closer to 29.4 meters per second. And just as a little note here, this is our position function. So some of you have probably taken calculus before and you may know how to take a derivative. So if you take the derivative of this number with the power rule and then plug in 3 for t, you will get 29.4. So right now we're making educated guesses, but it happens to be right. This actually is the instantaneous velocity. So a couple of notes here. First note is we are approaching 3 from the right. And what that refers to is, if you think of a number line, you've got a number line here. Here's 0, here's 3, here's 4. Well, we're approaching this 3 from the right because we're from numbers over here that are bigger than 3. We're using these numbers. These are all bigger than 3, so we're approaching from the right. We could have just as easily approached 3 from the left. So we could have instead, although we didn't, we could have started here at like 2 and tried things like 2.9, 2.99, 2.999, and get closer and closer to 3. That would be approaching from the left. We didn't. We could have. We would have gotten the same thing. The other note is Just that this process should look very familiar because this really is the same as the tangent problem. The tangent problem is more general. The tangent problem is just saying we're looking for the slope of a tangent line to a curve. Well, when that curve happens to be a position versus time curve, well, then you have average velocity. But that curve could literally be comparing any two variables. And then you'll be able to use the same technique to get some other thing other than average velocity. It could be something else. We'll see that as the semester goes on. And then we've got a little fill in the blank here. And this is in bold print, so it's got to be important, and it is. This says the instantaneous velocity is defined to be the limit of the average velocities over shorter and shorter time periods. So here's this idea of a limit again. Calculus does a lot with limits. It's a limiting value. As these time periods get closer and closer together, this appears to approach a number, and that number that it approaches, the limit of these average velocities, is the instantaneous velocity. And this is how we define it. And then it just mentions that we find the velocity of an object using the geometric idea of a tangent line. And we'll see that there are lots of applications that can be interpreted in terms of tangent lines. Even though a month from now we won't really think of these as tangent lines, they could all be interpreted in terms of tangent lines. So it's usually the way you approach it first. It's easy to get an intuition about what's happening when you think of a tangent line to a curve. Later on, we would not be thinking about tangent lines every time we take a derivative. We'll move away from that geometric interpretation when we get into other areas. So we've got one last example, and this one shouldn't give us too much trouble now that we've seen what's happening. So we've got this point, 3, 1, lies on this curve, y equals the square root of x minus 2. We've got this other point, q, and we want to find the slope of the secant line PQ to correct to 6 decimal places. We'll be using the calculator for this. The calculator can do all the number crunching for us. So we want to just think of a couple of things. We've got this point 3, 1, point P. We've got this point Q, which is going to be the point x and the square root of x minus 2 for any x, right? We just plug in various values of x. But in this case, they give them to us. They give us these values of x to plug in, and we just want to use the slope formula to find the slope. So the slope through PQ, of course, is just going to be y2 minus y1 over x2 minus x1, our handy slope formula from algebra class. And now if we use this formula with these 2 points, we'll get y2 minus y1, x2 minus x1. So this would be the square root of x minus 2 minus 1 over x minus 3. And of course, we're not going to be able to plug in a 3. But like before, we're going to get really close to 3 and then see if we can make an educated guess. So in the calculator, of course, what we want to do is go to the y1 screen and plug in x minus 2 minus 1. And make sure, depending on the calculator, we want to make sure we get order of operations correct. So in most cases, we need to use parentheses, unless your calculator has math print, where it actually makes the fraction. You have a numerator and denominator. And then once you have this in there, we just need to go to the table and punch in these values for x and see what we get for the slope. So if you go through this on your calculator, you should get these numbers here. I just rounded these to 6 decimal places, and then we can see as x approaches 3 from the left, from numbers below 3, you can see the numbers seem to be approaching 0.5. Then also as we approach 3 from numbers above 3, so approach from the right, it also seems to be, if you look in here, it looks like these are getting close to maybe 0.5. So if we had to guess, for part B says using the results of part A, guess the value. Well, if I had to guess, I would say it's probably 1/2. And once we learn how to take derivatives, we'll be able to see exactly what it is. But at this point, we're guessing. And once again, we happen to guess correctly. So it is 1/2 here. And then they want us to use this to find the equation of the tangent line to the curve at this point 3, 1. And again, there's 2 ways to do this. So some of you would have learned this technique, where we plug in what we know and we'll go right to the answer when we solve for y. And others would have learned this technique, where you find b. I'll do it both ways just to make sure everybody is okay on this one. So in this case, if I use this technique, I'm going to plug in 1/2 here. And the point I use is the point x1, y1. So I have 3 goes in for x1, 1 goes in for y1. So then we're going to get y minus 1 equals 1/2 x minus 3. Y minus 1 equals 1/2 x minus 3/2, right? Because I distribute the 1/2 through here. And then here I need to get y by itself, I need to add 1 to each side. Well, adding 1 is like adding 2 over 2, right? Since I got halves over here. So adding 1 to this side is like adding 2 halves here. So when you do that, you get y equals 1/2 x minus 1/2, right? Because minus 3/2 plus 2/2 gives us this. So this is our final answer. Over here with this technique, we're going to find b. So I plug in the slope, which is 1/2, and then I take the point 3, 1, plug this in for x, that in for y. And when we do that, we get 1 equals 1/2 times 3 plus b. So 1 equals 3/2 plus b. So to get b, I need to subtract 3/2. So this is like 2/2 minus 3/2. So I get negative 1/2 for b. So with this technique, we've got our answer. With this technique over here, now we know what b is, and we already know what the slope is. So then when we plug everything in, we'll get the same thing. Y equals 1/2 x minus 1/2. So that should give you everything you need to do the homework in section 2.1. And now it's just up to you guys to put in the work and let me know if you have any questions.